So here we are, 4 months in, give or take, to our data skeptic interpretability theme. I've learned a lot. I'm also at the stage where I'm going to pause and maybe think carefully about what I mean by certain words like interpretable or explainable or trust, trustworthiness. In fact, I feel a Venn diagram coming on, but I'm going to keep that at bay for just a little bit. On some levels, interpretability is just a formula. Do a logistic regression on some simple analysis. Tell me your coefficients. Oh, you have a strong positive weighting on history of employment. You have a large negative weight on bankruptcy, a small negative weight on late payments, positive weights on these intuitive ratios you came up with. Okay, yeah, I see how this works. But for the more complex models, the deep learning models, those learning a mapping, a function that is not so easily compressible, our best solutions to these types of problems today require massively parallel arithmetic computations. So can we describe how computer vision works? Sure. It's a bunch of layers of convolutions and pooling and yada yada. But what I'd really like to do is ask that network a question. Maybe even start with childlike questions. Why to everything? Asking why to everything eventually gets you to physics, but let's start with, why do you think that's a panda? Well, we've had some progress in that direction, but I don't think we're near the end of the line. In fact, the word I really need to work into that Venn diagram is conversation. So thanks to deep fakes, seeing is no longer believing. Maybe conversation is the truest test of them all. This week on the show, no, it's not the imitation game. I'll be talking to Dan Elton about his paper, Self-Explainability as an Alternative to Interpretability for Judging the Trustworthiness of Artificial Intelligence. This paper presents a novel framework that has really got me thinking more about interpretability and what I mean by it.
My name is Dan Elton, and I'm a staff scientist at the National Institutes of Health, working on deep learning for medical imaging. And I do have to add the disclaimer, though, that nothing I say here represents the views of the National Institutes of Health or the federal government.
And there's been a lot of, I would say, advancements. We're in maybe a renaissance era of computer vision for medical purposes, or at least what's your perspective on it?
Yeah, I think sort of an inflection point, a kind of breakout moment here, because there's a lot of systems for medical images that are reaching the level of the average radiologist or clinician. There's a lot of activity in startups and a lot of things being looked at right now by the FDA.
So I've always been curious about, I guess, the difference between the data science for fun. You go get a data set off some website, and sometimes it could have medical data and you solve something, which is great, but it's really there to learn machine learning. And it seems to me that's probably different from what happens in practice. Do you have any ability to speak to some of the nuances that are different for a real practitioner working on ML in the medical domain?
What I found was moving from working with small data sets and basically tabular data to medical image data is there's a lot of domain knowledge that you need to do it well. So there's a lot of implicit biases that have to be fed in. So you have to know how to pre-process the data, how to remove noise, and it gets very technical as opposed to just applying off-the-shelf models.
And given the, I guess, consequences or seriousness of using ML with medical applications, from my point of view, Amazon can do whatever they want when they're trying to sell me a product. If they make an error, it's loss of their revenue, perhaps. We can't make the same flippant comments about medical techniques. Do you notice that the adoption is slower or more practical, or are there any things that make yellow brick road accessibility for new techniques?
Yeah, well, fielding a system in the medical imaging domain is, I think, much harder than other domains because it has to go through a very lengthy approval process at the FDA. Then the key thing they look for is that it actually enhances clinical outcomes. So actually having the AI system actually improves doctors' decision making, and that's pretty hard to show. So there is a lot more work involved in actually getting something to market in medical imaging, but there are companies that are doing it
As you'd mentioned, the FDA, I don't know if that's their official mantra, but they're trying to increase clinical outcomes. That makes a lot of sense to me on the surface, but it feels like maybe lying underneath that could be a concern about overfitting and stuff like that. Are you aware of any of the techniques that, whether it's the FDA or the industry as a whole, has to take on, extra protections beyond the typical things that machine learning practitioners use?
Oh, well, overfitting is a huge concern. And one of the challenges is that in real world data can change. So, for instance, if you have a CT scanner and you upgrade it or you start using different parameters, your data can change. And one of the big problems in the field is actually that a lot of these models don't transfer between like images from different scanners. And right now, people are trying to figure out how do we build good test sets that cover the wide range of types of images that may be encountered in the wild. It's still an ongoing challenge.
The paper you authored that I most notably wanted to talk about on today's show is titled Self-Explaining AI as an Alternative to Interpretable AI. I guess let's start with interpretability. Do you have, whether it's formal or not, some definition that you work with for what makes a model interpretable?
Yeah, well, I actually differentiate two types of interpretation. So the first one I just call like an accurate interpretation, which just tries to reproduce the input-output mapping of the model. So this is sometimes done with like a post hoc model, like a linear model that reproduces the input-output of the network. The other type of interpretation or explanation I call a mechanistic explanation, and that attempts to explain actually how the model is functioning internally. In my experience, that's much more difficult and much rarer to find.
Gotcha. But presumably more desirable, yeah?
Yeah, I think it's very desirable to ensure trustworthiness because, for instance, in medical imaging, it would be really useful to know that the way the model is operating is a way that is known to be robust by radiologists. Or ideally, it would be similar to how a radiologist would do the task, which we know is fairly robust. But what we're finding, though, is that the way these deep neural networks are operating is actually very different than the way radiologists would analyze a medical image. And I think they're doing largely interpolation, which means they're not going to extrapolate to new circumstances the way a radiologist would. And that's kind of my big concern about deep learning right now.
What do you mean exactly by they just interpolate?
This ties into the phenomenon of double descent, which I think is critical to understanding how deep neural networks function.
I don't think all of my listeners will know the term. What is double descent?
Double descent is basically a breakdown of the bias variance trade-off that you find in a lot of textbooks on statistics or machine learning. And so it's really interesting because what has been found recently is that normally as you increase the capacity of a neural net, like by adding more layers or more neurons, the test error will initially decrease, but then at some point you start overfitting and the test error will start to increase. And so that's like the classical bias variance trade-off, which I'm sure a lot of people are familiar with. But what's been found recently is that if you keep increasing the network, then that test error stops increasing, actually peaks, and then starts decreasing again. And that's what they call a double descent. So what happens is that at a certain capacity threshold, the network actually becomes able to interpolate the training data almost perfectly and without like the undershoot or overshoot that we often associate with overfitting. And so it's believed that most deep neural networks actually operate in this regime of interpolation. And I think this is a really fundamental thing to understand because if a neural network is functioning purely through interpolation, that means there's no guarantee it's going to extrapolate. And so we have to be very careful when we're applying these models. We're not going outside of the domain it was trained in. In other words, we're not trying to extrapolate outside of the domain of the training data. I have seen this problem firsthand in medical imaging where the deep neural networks cannot deal with anomalies that might be in the image, which would not cause any problem for a radiologist. So for instance, implants, say like the hip or the spine, can confuse these deep neural networks. Even if they're trying to do something which is trying to identify something in a very different part of the body, just the presence of this thing in the image that it hasn't seen before can be enough to disrupt the model's functioning.
And you'd said earlier that some of the, I guess, techniques, I'm not quite sure what the right word is, but the mechanisms by which models have achieved some level of accuracy in medical imaging is often somewhat fundamentally different from how the actual radiologist would look at it. How do we know that?
In my paper, I give one example. Of course, I don't know how much you can generalize from that, but the past 6 months or so, I've been focused on identifying a certain vertebra in the spine called the L1 vertebra. And that's because we want to do an automated measurement inside that vertebra. And so the way that a radiologist would identify this vertebra was they would look where the ribs are and they would look at the lowest rib, and the vertebra attached to that is called T12. And then the L1 vertebra is right below that. So they would look at the ribs and then basically drop down one level to the L1. But my sense is, given the brittle nature of these neural networks, that can't really be what they're doing, because these networks often are confused by the presence of other things in the image. I don't think we can assume they have an understanding of anatomical concepts.
Yeah, one of the examples I see a lot of researchers trying for interpretability in computer vision is these sort of like heat map overlays that highlight, what are the important areas you looked at. And so perhaps identifying that someone's a lumberjack highlights that they're holding an axe, and that seems to give us pretty good, comfort level that it's done something smart. But I've never encountered yet a model that spits out a sentence saying, I found the lowest vertebra and I went one below it, which is kind of elegantly simple, I guess. What's the state of research headed in that direction look like?
Well, people are generally in agreement that being able to explain the model improves trust. But in my mind, the explanation really has to map onto how the model is actually working. And so my concern is a lot of these explainability techniques, while they're maybe saying something at a high level, they're not getting into the weeds of how the model is actually working. So in my paper, I explored this idea of, instead of trying to explain the model like post hoc or using some kind of explainability method that probes the model's input output, it may be better to actually try to have the model provide an explanation itself. So I call it self-explaining AI. And there's been a bit of work on this, but in my mind, there's a lot of work that still needs to be done. Some of this work actually has some issues, because one of the issues with having a self-explaining network is you need to be able to know that the explanation actually is related to how the, say, diagnosis is being done. And I don't really see current networks which provide these kind of self-explanations actually doing that.
So I guess something I could do as a programmer is run a machine learning algorithm, and then after I have my model, run something like Lime or SHAP values or a lot of these popular interpretability tools that are out there, and bundle those two outputs in a zip file and say, there you go, it's self-explaining. It's the model and this interpretability thing. Is that self-explaining AI, or is there something more that should be used, like that term self-explaining?
So a lot of these techniques, like Lime in particular, I view as sort of post hoc. So that means that you're fitting an approximate model. So sometimes that's a local model, like in case of Lime, or sometimes it's a global model, like trying to distill it into a decision tree or something like that. But the issue I have with it is you're dealing with an approximation. So there may be important things that are missing. I think people are realizing now with Lime in particular, there's some other issues with that, like not being robust to small changes. And also, there's a parameter in Lime, which is sort of like the kernel width, I think it's called. And so they found it's sometimes very sensitive to that tuning of that parameter. That said, I still think it can be useful to some extent for, specific cases, getting an understanding of what's going on. But I don't think you can generalize necessarily from looking at a few Lime outputs to saying you really understand how the model is functioning.
So, what might a richer, more robust, self explaining AI explanation look like?
I feel like in this paper, I kind of just scratched the surface of what might be possible here. Ideally, there would be an output from the neural net that actually is human understandable, which would engender some more trust or confidence in that the neural network actually understands things in a way that would be robust to irrelevant changes in the image. There hasn't been a lot of work on that, but that's what I would like to see ideally.
I would say that the paper really presents like a framework to describe the general formalism of which many people could come up with variations, and they'd all be under sort of an umbrella heading of this is the structure of self explaining AI systems. Is that a fair description?
Yeah, definitely, definitely. And like I said, this is just like an initial work. One of the challenges is making sure the explanation actually maps onto the functioning of the neural net. And so one of the things I look at is if we might be able to use mutual information to confirm that the explanation is actually related to the prediction.
If you wouldn't mind, I'd love to delve into what mutual information is. I think maybe listeners will know about the Pearson's R squared correlation or things like that, the relationship between two values. Not everyone knows mutual information. Why pick that over a simpler metric like the Pearson R coefficient?
R squared or Pearson correlation can't deal with nonlinear relationships, whereas mutual information can. Mutual information is great because it can detect any kind of nonlinear association between two variables. The issue with it, and the reason it's not used much, is that you have to sample over the entire, space of possibilities, the whole entire distribution, and that can be computationally expensive. So that's why it's not used a whole lot, even though in my mind, it's definitely superior to like Pearson correlation.
Could you talk a little bit about how that might help us get at this really good objective that we'd like the explanation to actually describe the model? How does mutual information help us do that?
So what I look at in my paper is a kind of a simple self-explaining neural network where you have a basic neural net and then you have two branches. One of them is for diagnosis and the other one is for the explanation. And we want to show that the diagnosis and the explanation are actually related. So we look at the latent layer right before the two branches branch apart. And I look at the mutual information between nodes in that latent layer and the explanation output and the mutual information between the nodes and the diagnosis and see if there's some overlap, which nodes share mutual information with both. There's probably better ways to do this, but this is just something that came to mind as one possibility.
And I also liked your stated objective that you'd like the explanation to be satisfying to the domain expert reviewing it. How do we, regularize for that without asking for too many labels from our human experts?
So you're asking, like, how would we actually verify that this is providing something that's useful or that's relevant to the end user?
Yeah, I guess there's in general maybe two approaches. One is you have direct feedback. So let's hypothetically say humans were a commodity and we could just call some API like the Mechanical Turk or whatever. Is this a satisfying explanation? You could ask that question at scale, perhaps, but that seems impractical. Maybe another approach is you have some methodology that presumably gets us there. Just was hoping to get your thoughts on how we deliver on that promise.
Well, you have to make sure it's relevant to the end user. And that's kind of part of the impetus for this to begin with. So I think you have to tailor the explanation to each domain and the subject matter experts that are going to be using the system. Other than that, I haven't really thought about how to actually formally verify this approach. That's definitely an interesting area to think about, though.
And I'm curious, what is your feelings on the phrase black boxes?
Yeah, one of the things I mentioned is just sort of a gripe I have with that term because technically speaking, we do understand all the internal functioning of neural nets unless it's hidden from us for some intellectual property reasons or something. Typically, you can see all of the weights and the entire architecture of these models, and you can trace through exactly all the computations that are occurring. So they're not really black boxes in the technical sense. And the other thing is, I think we do have a high level kind of explanation or understanding of how these neural nets are working in terms of the way that they're trained. So there was a really interesting analogy between training neural networks or optimizing them and the process of evolution. So that's another thing I talk about a little bit. And that's drawn from a really interesting paper called Robust Fit to Nature. And in that paper, they draw an analogy between neural network training and evolution. And so both are optimizing system for some objective function. In the case of evolution, it would be survival. Using the theory of evolution, we can explain animal behavior in terms of the needing to satisfy this objective function. And so in a similar way, we can explain neural nets, or we may be able to explain them to some extent, just based on looking at the training method, the learning rules, and the objective function that was used. That's an interesting idea, which I call meta-level explanation, which isn't really going into the details of what's going on internally in the neural network, but you're getting some high-level understanding.
Yeah, and you'd also pointed out we sort of have one really good example of AGI, and that's the human brain. And the path nature took to get to it produced what is ostensibly, I guess we could call it a black box. I mean, we can measure things about it, but it is not itself self-explaining. Should we expect machine learning to be self-explaining?
Yeah, well, another thing they talk about in this paper called Robust Fit to Nature is that the discovery of the double descent phenomenon and this interpolation is actually getting neuroscientists to rethink about how the brain functions. So they're starting to think that the brain actually is doing a lot of this brute force interpolation. And so a lot of these paradigms in cognitive neuroscience where they're trying to find simple features or simple stories about how the brain functions may be sort of barking up the wrong tree, because it may be inherently that it's just doing a brute force interpolation over massive amounts of data rather than using like one or two heuristic rules for things. So the point of that is they're saying that the brain is actually maybe a lot more like these black box neural nets than we thought. But what I find interesting is we are able to trust each other. And I think that's in a large part because we give explanations for our decisions and actions. That makes sense.
Earlier, we touched on the famous bias variance trade off, which anyone who doesn't know can go look up. It is a rigorous statistical proof. There's a derivation. Maybe others have also heard of this accuracy interpretability trade off, which, to the best of my knowledge, has no such derivation. How formal do you think this idea is? Is there truly an accuracy interpretability trade off?
It's definitely not very rigorous, but I do think there's an element of truth to it. There's a really interesting paper by Cynthia Rudin where she argues that the accuracy interpretability trade-off is a myth. So in that paper, she argues that for any given machine learning task, if you search the space of models enough, there should be an interpretable model. And so she's arguing there that we should be trying to move to these interpretable models instead of trying to explain black box neural nets. And I think for a lot of fields, she's completely right. However, I think when you get into dealing with very complex real world data, because the data itself is so complex, the model is also going to be very complex. So that's one point. And then the other point is just empirically, it seems like deep neural nets are sort of necessary for certain tasks. So for instance, in computer vision, medical imaging, all of the best performing networks are of this very deep, hard to interpret type. And then if you look at like the limiting case of, say, the human brain, then you're getting to something which is very hard to understand and explain. So I think when you get into very complex problems, it's going to be hard to find interpretable models. So there is some truth to this trade-off, but generally I think it's oversold, overused, and actually can cause a lot of misunderstanding, because another point is interpretable models, so-called interpretable models, can be very complex and hard to interpret. So, for instance, just very large decision trees can be very hard to interpret.
Definitely. And theoretically speaking, how might a self explaining AI network balance something like this if it's controlling both its output and what it's giving you for an explanation? Do you envision any sort of mechanisms there or tricks that might help a researcher do something clever to make sure the network gives us a satisfying output for both?
I haven't really thought about that a whole lot. There is a field of research now which is trying to learn interpretable models. So, like learning certain types of linear regression over very large, high dimensional spaces. but I don't think those are going to be transferable into dealing with real world image data and other things. So I think that the models are going to be fundamentally difficult to explain. A lot of these models, you're not going to be able to explain how they're actually functioning in terms of a couple rules, because the way they're working internally is actually basically memorizing training data, just doing a brute force interpolation. There's no way to really distill that into a few rules. That's kind of the impetus for trying to have this explanation output branch as well. So you at least have some assurance that the model is capable of understanding the relevant concepts or what are considered important or relevant concepts.
Yeah, I'd love to also explore that explanation output branch. I guess it could vary by the implementer and what the use case is and all that, but could you perhaps speculate on what that output might be like? Should we expect some sort of standard dashboard of, flags that indicate or an English sentence? What kind of things can we generate?
Well, conceivably, you could have an RNN that generates an English language output. There was actually some work in our lab from a couple years ago called TINET, which was trained jointly on chest x-ray images and medical reports. So it would look at a chest x-ray and it would actually output a medical report or doctor's notes. That's one possibility. Another would be having some explanatory features. So, for instance, there's a data set for lung nodule cancer diagnosis where they've also provided labels for several features that are deemed relevant. So, they also call these attributes. And some of these are like sphericity, texture, granularity, things like that. Could be either like a text output or just a couple of these attributes that are deemed relevant.
Are there any barriers, like you'd mentioned the compute cost of doing mutual information because of the sampling required? Are there any barriers that need to be overcome for techniques like self explaining AI to become more popular?
I think that the mutual information calculation should be quite feasible, and you only have to do it once. You just loop over your training data and basically check this mutual information overlap. What I do see being a little bit difficult, though, is the uncertainty quantification. So in the paper, I also argue that you need uncertainties for both the diagnosis and the explanation. I've always been a big proponent of uncertainty quantification, but unfortunately, there it can be tricky. There is a way of estimating the Bayesian uncertainty using dropout, which is pretty cool. So I think that should ideally be used. But if you want to have a fully Bayesian network that gives you the Bayesian uncertainty, that's very expensive.
The paper in a couple places touches on the role of a domain expert, which makes a lot of sense to me. In medical imaging, I doubt if any self explaining AI would be satisfying to me because I don't have medical background. It really should be aimed at the doctor or the radiologist or whomever. I guess what's the relationship between applicable domain and maybe transfer learning?
So applicability domain is a very simple concept. It's just the domain in which your model achieves a high accuracy. So, you could have some threshold, I guess, where like within this input parameter space, the model is going to have at least a certain accuracy on average. The goal of transfer learning is really to expand the applicability domain so that a model can perform sort of on two different data sets. So like you might be taking a model trained for images without contrast agent or contrast enhancement, and then transferring that model so it also can function on images with contrast, just as an example. So that would be expanding the domain under which the model can function. You could also be trying to do a different output for your diagnosis or prediction. So that wouldn't really change the applicability domain, but it would change the outputs it's giving. The applicability domain is really limited by the data set. And so one way of thinking about it just crudely is that if you picture all your data points, your training data points in some high dimensional space, generally speaking, the model is going to function when it's within that distribution. And then when you go outside that distribution, typically the model is not going to do as well. So it's not going to extrapolate. And so one crude way of defining the applicability domain is just looking at a convex hull of your training data in whatever high dimensional space it lives in. And I've just been surprised I haven't seen this concept discussed much in a lot of the literature. Interestingly, it is discussed heavily in the specific area of molecular property prediction. There's an area in chemistry called quantitative structure property relationships that is a few decades old. In that area, they want to make sure they're very careful to quantify and delineate the domain of applicability. So when they train a model to, say, predict a certain property like binding affinity to a receptor in the body, in that particular field, they also quantify in some way like what types of molecules the model will function for. In that particular field, there's actually a number of papers reviewing many, many different methods for doing this applicability domain analysis. The convex hull method is just one. There's many others. It's interesting that I haven't seen this discussed much outside of that particular field, even though it seems like it would be very relevant to ensuring robustness. If a model also ships with applicability domain analysis kind of component, then the model can provide like a red flag when it's operating outside of its applicability domain. And this is important to do because models that are operating outside of the domain they were trained to operate in, even if they have uncertainty quantification, the uncertainty quantification will also not be reliable. Models can be very confident that they are correct and be wrong if they're operating outside the domain they were trained in.
Yeah, that's an interesting property we don't see in a lot of human users. Usually, if we're wrong, we're not confidently wrong, or at least one would hope, I guess. How do we expose that in your vision for the architecture? Is there a variable or an output? Can the machine convey the degree to which it's confident in its answer?
I definitely think you should have the uncertainty quantification, but it also needs to be supplemented with this applicability domain analysis of some type. And there's a huge literature on this. I'm not really an expert on it. The convex hull method is just one method, but there's a lot of other methods like fitting certain Gaussian functions. I can't remember exactly what they are, but if you look at my paper, I referenced some reviews on this subject, which actually I'm going to be looking into further because this is, I think, from my next thing I'm going to be exploring more is this concept and how it can be useful for improving robustness.
Yeah, I look forward to seeing what you come up with. This is a very interesting area of research. Where's a good place for listeners to follow you online?
They can definitely follow me on Twitter. My Twitter handle is more is different. They can also just email me, daniel.elton@nih.gov, because I would really appreciate feedback on this preprint. Still a work in progress, and feedback would be greatly appreciated.
Great. Well, I hope you hear from some people. We'll definitely have links to all that in the show notes. Dan, thank you so much for sharing your thoughts in the paper and coming on again to discuss them here.
Yeah, thank you, Kyle.
You've been listening to Data Skeptic Interpretability. Our guest this week was Dan Elton. Our theme song is Number 5 by Big D and the Kids Table. Thanks to our sponsor, Brilliant.org. Head over to brilliant.org/dataskeptic to let them know we sent you. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. And I've been your host, Kyle Polich. Stay in, stay safe, and learn some data science while you're at it.